Now that we've seen some examples of series and we've had some practice working with sigma notation, let's take a look at one very important special kind of series, which is a geometric series. A geometric series is a series in which each term is a constant multiple of the preceding one. This is a geometric series. We've actually seen an example of this. We saw the series 1/2 plus 1/4 plus 1/8 plus 1/16, and we use that square trick to show that this series actually adds up to a finite value of 1. This is a geometric series because between each term we multiply by 1/2 to get to the next term. So 1/2 times 1/2, 1/4. 1/4 times 1/2, 1/8. 1/8 times 1/2, 1/16. So this is a geometric series. Each term is a multiple of the preceding term. In other words, we can get to the next term by multiplying by some constant value. This constant r is called the common ratio. An infinite geometric series has this kind of a form. If you look at these different terms here, each one is being multiplied by this common ratio r. A times r, ar. Ar times r, ar squared. Times r again, ar cubed. So this is the generic form for an infinite geometric series. We would like to answer the question of whether or not a geometric series converges. We've seen one example of a convergent geometric series, but here's an example of a series that does not converge, that is still geometric. 2 plus 4 plus 8 plus 16 plus 32. This is also a geometric series. Here we have a constant ratio of 2. Multiply by 2 each time, and you get to the next term. But this does not converge to a finite value. If we add up all these numbers, that just goes off to infinity. Therefore, in some instances, we have convergent geometric series. In other instances, we have divergent geometric series. How can we tell the difference? The key is to look at the value of the common ratio. If the absolute value of the common ratio is less than 1, then the geometric series converges. And if it converges, we can actually find its sum. The sum is given by a divided by 1 minus r. A is the first term, and r is the common ratio. So rather than use this expression for the sum of a convergent geometric series, I like to think of the sum simply as the first term divided by 1 minus the ratio. If we think of the formula this way, then we get away from trying to determine what's a, what's r, and trying to make sure that the form fits into this expression here. So when we know that we have a geometric series, as long as the common ratio has an absolute value less than 1, we can find the sum simply by finding the first term of the series and divide by 1 minus whatever that common ratio is. So use this expression to find the sum of a convergent geometric series. If the common ratio has an absolute value of greater than 1 or equal to 1, then the geometric series diverges. Using this, we can tell exactly when a geometric series will converge or diverge. For this example here, the ratio was less than 1 because it was 1/2, so we have a convergent geometric series. In this example, the ratio is greater than 1, therefore this geometric series diverges. Let's work through some examples so that we can master the topic of geometric series. In example 4, we have a bunch of series listed out. And our first step is going to be to determine whether or not the series is geometric. If it is geometric, we want to find the common ratio to help us to determine if the series converges. If the common ratio has an absolute value of less than 1, then the series will converge and we will want to find the sum. So let's practice on these different series. For example 4a, we have the series n equals 0 to infinity of 3 times n. First, we want to know if this is a geometric series. Well, to determine if it's a geometric series, we need to figure out if there's a constant ratio. We might be tempted to think, well, maybe it's 3 because we have this 3. But to figure that out, let's write out the first several terms. This series starts with n equals 0. So the first term is actually 0 here. And then when n equals 1, we have 3 times 1, 3. If n equals 2, we have 3 times 2, 6. If n equals 3, that would be the next term. We have 3 times 3, 9. So we have 3 plus 6 plus 9, etc., etc. Is there a common ratio here? Here's how we can tell. Let's take two consecutive terms and look at the ratio. 6 divided by 3, that's 2. So in order for this to be geometric, we would have to have the same ratio from the term 6 to the next term. So if I multiply 6 by this ratio of 2, I would get 12, which is not 9. So this series is not geometric. There is not a common ratio between the terms. Let's look at the next series. For part B, we have the series from 0 to infinity of 3 raised to the n power. So again, let's look at the first several terms. 3 raised to the 0, well, anything raised to the 0 is 1, so we have 1. 3 to the first is just 3. 3 squared is 9. 3 to the 3 cubed is 27. And this continues. Do we have a common ratio here? Let's again look at consecutive terms. To get from 1 to 3, we multiply by 3. So we have a ratio of 3 between these terms. To get from 3 to the next term, do we have the same ratio? Well, yes, because if I multiply 3 by 3, I get 9. So I have a common ratio of 3 here. Also from 9 to 27, another common ratio of 3. So yes, this is geometric. Does this geometric series converge? Well, the common ratio here is 3, and because that ratio is greater than 1 in absolute value, this series does not converge. So this is a geometric series, yes, but it diverges. It does not converge to a finite value. How about letter C? This is the series, again from 0 to infinity, of 1 divided by 3 to the n. So we're just going to take these same numbers here, but now they're going to be in the denominator. So we have 1 over 3 to the 0 is just 1. So our first term is again just 1. Plus 1 divided by 3 to the first, that's 1/3. Plus 1 divided by 3 squared. Plus 1 divided by 3 cubed. Again, going on to infinity. This is an infinite series. Is it geometric? Well, again, I look at the ratio between the consecutive terms. To go from 1 to 1/3, I multiply by 1/3. And do I have that same ratio between these next two terms? If I multiply 1/3 times 1/3 again, do I get 1/9? Oh, yes, I do. So from 1/3 to 1/9, I have the same ratio, the same between 1/9 and 1/27. So I have a common ratio here of 1/3. So yes, this is geometric. The common ratio is 1/3. Does this geometric series converge? Yes, it does, because the common ratio is less than 1. So it converges. Let's figure out what it converges to. The sum for a convergent geometric series is the first term divided by 1 minus the ratio. That's the best way to think of the formula for the sum of a convergent geometric series. My first term here is 1, and my ratio is 1/3. I just plug those into the formula. So I have first term, 1, divided by 1 minus the ratio, 1/3. 1 minus 1/3 is 2/3, so this is 1 divided by 2/3, and then this simplifies to 3/2. So this series, even though it's infinitely many finite numbers being added together, this series adds up to a finite value of 3/2. It is a convergent geometric series. Take a look at part D. For part D, we have the series 1 plus 2 plus 3 plus 4. Is this a geometric series? Again, we want to look for common ratios. From 1 to 2, we have a ratio of 2 because I just multiply by 2. To go from 2 to 3, do I have a common ratio of 2? Well, no. If I multiply 2 by 2, I get 4. I don't get the next term 3. So is this a geometric series? No, it is not. This is not a geometric series. Let's keep practicing with letter E. For letter E, I have the series where n is greater than or equal to 1, and I'm adding up 12 divided by -5 to the n. This notation looks a little bit different from what we're used to, but this sigma notation with the n greater than or equal to 1, this is the same as saying that n starts at 1 and goes to infinity. So really these two pieces of notation are the same. I can say that n is greater than or equal to 1, or I can say that n begins at 1 and goes to infinity. They're both the same. So I can expand out several terms here. I'd start with 12 divided by -5 to the first, which is -5, plus 12 divided by -5 squared. -5 squared is 25. and then 12 divided by negative 5 cubed. I'm back to negative again because I have negative 5 to a odd power. So this would be 12 divided by negative 5 cubed, which is negative 125, and it keeps going. Can you see a common ratio here? How do we get from one term to the next? Is there a common multiple? Well, yes, there is. And the common multiple is negative 5 in the denominator. So we have a common ratio here of 1/5, negative 1/5 actually. If I multiply by negative 1/5, multiply the first term by negative 1/5, negative times negative gives us positive, and then I still have 12 in the numerator, 5 times 5, 25. If we multiply 12 over 25 by negative 1/5, we now get something negative. Multiply the 5 times 25, 125. So yes, this is geometric. Is it a convergent geometric series? Well, look at the common ratio. Does it have an absolute value of less than 1? If I take the absolute value, I get 1/5, which is less than 1. So yes, it converges. What does it converge to? Well, it converges to the following formula. We take the first term, divided by 1 minus the ratio. What is the first term here? It's simply 12 divided by negative 5. So we take 12 divided by negative 5, divided by 1 minus the ratio. The ratio here is negative 1/5. So 1 minus 1/5 is 1 plus 1/5. And we could simplify a bit here if we want. 12 divided by negative 5. 1 plus 1/5, that's 5/5 plus 1/5. That's 6 over 5. So 6 over 5. Now we could cancel these 5's here, but we retain the negative. So negative 5 cancels with that 5, and we would have negative 12 divided by 6, which is negative 2. So this geometric series adds up to the finite value of negative 2. It is a convergent geometric series, and we just found that the sum is negative 2. Let's work through letter F. We have the series 3 minus 4 plus 16 over 3 minus 64 over 9 plus etc., etc., etc. Is this a geometric series? Let's try to find out. We want to take the ratio of common terms, or consecutive terms, and see if we have a common ratio. So we're going to start with negative 4 divided by 3. That's the ratio between the first two terms. I can go from 3 to negative 4 simply by multiplying by negative 4/3. So I have this common ratio between the first two terms. Do I have the same ratio from negative 4 to 16/3? Well, negative 4 times negative 4/3, negative times negative would cancel. 4 times 4 is 16 divided by 3. Yes, I have the same ratio between these two terms. How about the next two? Do I have a common ratio of negative 4/3? 16 times negative 4, that is negative 64. And then 3 times 3, that's 9. So yes, I do have a common ratio here. The common ratio is 4/3. So this is a geometric series. Is it a convergent geometric series? Well, look at the absolute value of the common ratio. Here's our common ratio r. The absolute value of r is greater than 1. It's 4/3. So because the absolute value of r is greater than 1, this diverges. It is not a convergent geometric series. We have two more examples to work through here. Take a look at 4g. For 4g, we have the sum, where k goes from 3 to infinity. 2 to the k times 3 to the negative k. Is this a geometric series? Well, we could start by just listing out the first several terms as we've been doing. But let's first try to rewrite the series and see if we can recognize it without having to write out all the terms. I have the series from 3 to infinity. I'm going to rewrite 3 raised to the negative k as 1 divided by 3 to the positive k. So I can write this as 2 to the k times 1 over 3 to the k, or just divide by 3 to the k. The negative exponent goes downstairs and becomes positive. I have the same exponent in both the numerator and the denominator. And because I have the same exponent, I can just write 2/3 to the k. This simplifies as the sum, k goes from 3 to infinity, of 2/3 to the k. If we were to write out the first several terms, we get 2/3 cubed plus 2/3 to the 4th plus 2/3 to the 5th, etc., etc. We have a common ratio here of 2/3. So the ratio here is 2/3. So yes, it is geometric. Is it a convergent geometric series? Well, look at the ratio. Does it have absolute value less than 1? Yes, it does. 2/3 is less than 1. So yes, it converges. Let's find the value that it converges to. It converges to the first term divided by 1 minus the ratio. That is the sum of this convergent geometric series. The first term is what I get at the very start when I first plug in 3 for k. So let's just write out maybe the first two terms. If I plug in 3 for k, I get 2/3 cubed. The next term would be 2/3 to the fourth, and I have infinitely many terms. We can see the common ratio here of multiplying by 2/3 to get to the next term. The first term is 2/3 cubed. So this sum, if I write the first term divided by 1 minus the ratio, I have 2/3, the whole thing cubed, divided by 1 minus 2/3, and let's just simplify this. 2/3 cubed is, well, 2 cubed is 8, 3 cubed is 27. So we're going to have 8 divided by 27, divided by 1 minus 2/3 is 1/3. And if I divide fractions, I have 8 over 27 divided by 1/3, so multiply by the reciprocal, times 3 over 1, and this simplifies the 3 and the 27 here. I can cancel a factor of 3, and I have 8 divided by 9. So 8 over 9 is the sum of this convergent geometric series. Finally, look at 4h. For 4h, we have 1 over 6 plus 1 over 9 plus 1 over 12 plus 1 over 15. First of all, we want to establish whether or not this is a geometric series. To figure out if this is geometric, we take the ratio of consecutive terms. So first I'll look at 1 over 9 divided by 1 over 6. I'll look at the ratio between these and see if I have the same ratio between the next two terms. So 1 over 9 divided by 1 over 6. Division of fractions, I can just invert the denominator and multiply. So 1 over 9 times 6 over 1, and this simplifies to 2/3. So I have a ratio of 2/3 between the first two terms. Do I have the same ratio from 1/9 to 1/12? Well, let's check. If I take 1/9, multiply by the ratio 2/3, do I get 1/12? I get 2 divided by 9 times 3, 27. 2 divided by 27 is not the same as 1/12. So I don't have the same ratio between these second two terms. Because I don't have a common ratio between all the terms, this is not a geometric series. Now that we've had so much practice with geometric series, let's take a look at example 1 again. This is a geometric series. We have a constant ratio of 1/2. So let's find the sum without using this geometric argument, as cool as it is. Let's find the sum using the formula. So here we have the common ratio of 1/2, and the first term is also 1/2. So the sum for this convergent geometric series is first term divided by 1 minus the ratio, which would be 1/2 divided by 1 minus 1/2. 1 minus 1/2 is 1/2. I have 1/2 over 1/2, and that equals 1. Using the formula for the sum of a convergent geometric series, we have the same value as what we got from this geometric argument. So this makes good sense. One thing we haven't done with geometric series is see why this formula gives us the sum of a convergent geometric series. So we've seen that if the ratio is less than 1 with absolute value, then the geometric series converges, and it converges to this a over 1 minus r, or as we like to use the formula, first term over 1 minus the ratio. But why does this formula work? Why is this true? Let's go ahead and work through a little proof to verify that this formula works. I want to prove that a plus a times r plus ar squared plus ar cubed, etc., equals first term a divided by 1 minus r. I want to prove this, assuming that the absolute value of r is less than 1. How can I prove this sort of a statement? The first thing I'm going to do is imagine dividing both sides here by a. If we divide both sides by a, or we can just think of canceling a from both sides, then really this formula is actually equivalent to the following: 1 plus r squared plus r cubed plus etc. equals 1 over 1 minus r. These two expressions are equivalent. So I'm actually going to prove this statement here, and then once I've proved this statement, I can simply multiply both sides of this expression by a rather, and we'll get the original statement here. So I'm going to work on proving this equation, and then just multiply this equation by a, and we'll have the exact formula that we want. Let's start by calling this sum just s. So we're going to start by letting s equal 1 plus r squared, etc., etc. I'm not assuming anything about s at the moment. I'm just assuming that s equals this value. I'm just defining s to be 1 plus r squared. And what I want to do is show that s turns out to be equal to the other side of the equation, 1 over 1 minus r. So I want to show that s equals 1 over 1 minus r. If I can prove that s equals 1 over 1 minus r, well, then I've proved that these two things are the same, and that's what I'm trying to do. How do I get there? It's actually quite simple, and it's really cool. I hope you'll appreciate this trick. It's a really nifty little proof. I'm going to take this infinite series, and I'm just going to multiply both sides of the equation here by r, the common ratio. So on one side, I have r times s. And on the other side, I multiply r by all these terms here. So r times 1 plus r times r plus r times r squared. And what I get, I just have r times 1 is r. And then r times r squared. R times r squared, r cubed. And it keeps going. At this point, I'm going to subtract these two equations. So I can imagine taking the left-hand sides here and subtracting those. And I can imagine taking the right-hand side, subtracting those. So s minus r times s, that's just s minus rs. I have that on the left-hand side. Now look what happens when we subtract these two sides. We have 1, I'm going to think of kind of lining these up like this. 1 minus nothing, so that just gives me 1. And then r minus r, well, those would cancel. R squared minus r squared, those cancel. I'd have an r cubed here, which cancels with this r cubed. All of the terms moving forward are going to cancel when I subtract these two expressions, because I have r plus r squared plus r cubed plus r to the fourth, and I have r plus r squared plus r cubed plus r to the fourth. Those all cancel out. So what am I left with on the right-hand side? I'm just left with 1, because all of these common terms just cancel right out. So I have this simpler expression here. I don't have an infinite sum anymore. It's just s minus r times s equals 1. On the left-hand side, there's a factor of s. I can just factor that out. And I have s times 1 minus r equals 1. Now divide both sides through by 1 minus r, and we're left with s equals 1 over 1 minus r. Look at that. That's exactly what we wanted to show. We just showed that s equals 1 over 1 minus r. And what is s? By definition, s is this infinite series. So we showed that s equals this, and also the other side. Therefore, we have the equation proven. Multiply both sides of this by a, and we get the original equation for the sum of a convergent geometric series. Isn't that a cool proof? I think that's just a really nifty argument.